Good morning, my dear student. Today we are going to learn fifth problem in machine design. Find the maximum normal and shear stress for combined loading on a member as shown in a figure. Let us see on this the first force. The force 15 kilonewton is acting at this point, or we can say as acting on axis. They making the angle of 60 degree with the horizontal component. They making the angle of 60 degree with horizontal component. Okay, dear. If you want to resolve, let us see. I will rub this one. I will resolve this figure. Axis A component and this one is B component. The diameter of this beam or structural member is 50 mm. Okay, the torque is acting on this component is torque T equal to 1 kilonewton meter. So this means that 1 kilo means 10 power of 3 Newton meter. If you want to convert in millimeter means 1 into 10 power of 6 Newton millimeter. Okay, dear. Again, let us see the force. Which type of the force is acting here? The compressive force. The compressive force is acting at a point of O. Let us assume this point is O. Okay, which force is acting? Compressive force. 15 kilonewton. If you resolve horizontally, okay, as well as vertically. Okay. If you want to resolve horizontal and vertically, so 15 kilonewton is acting at a point of O. They resolve in the two direction. One is horizontal, another one is perpendicular. So horizontal, how it is making the angles? Let us see. 15, the force, it is a form of F cos theta, horizontal. Because the force 15 kilonewton, they making the angle of 60 degree with the horizontal means the one we have to resolve in such a way that horizontal F cos theta, vertical F sin theta. Okay, dear. The force how much is acting at the point of O? Force is acting as 15. How much they making the angle? 60 degree. Cos 60. Okay, what about here? 15 sin 60. Okay, dear. So this means that 15 cos 60, which load is there? It is assumed as axial load is acting at a point of O. And what about the 15 sin 60? So bending load is acting at a point of O. Okay, axial load is how much is there? 15 cos 60 is acting at a point of O. The bending load 15 sin 60 is acting at a point of O. And torsion, how much is acting? 1 into 10 power of 6 Newton mm. Okay, so this means that on this component the several forces acting. The first one we are going to learn about axial load. So I will rub this one. So length is how much is there? 250 mm. Okay. Let us see. First one we are going to learn about axial load. axial load acting. Okay, first you need to draw this figure. A and B. Axial how much is acting here? 15 cos 60. Okay dear, axial load is acting. What is the nature is there? Compressive nature. Okay dear. And then diameter is how much is there dear? Diameter is 50 mm is given. If you want to draw distribution load diagram, okay, let us see. Distribution load diagram. Okay, which force is acting here? Compressive force is applied in the form of action. Then reaction will come from opposite order. Is it right? So what we can say, this one we can say as active force is applied. Okay, how much force is there? The force is in the form of 15 cos 60. Okay, what about here? Again this one we can say as reactive force is applied on this component. Okay dear, what is the diameter? Diameter of this specimen is 50 mm. Section A and B. Okay dear, again if you want to draw the free body diagram also, then again how many force? Like this. This is the load distribution diagram. If you want to draw the free body diagram, the same figure you need to represent compressive force. That's it. The nature is compressive. You have to represent as minus. Okay dear. Then on the section A and B. After that we need to find out the tensile stress. We need to find out in this section. First you need to find out the cross section. Cross sectional area. Okay dear. So area formula is A is equal to pi by 4 into d square. Pi by 4. Diameter is how much is given here? Diameter is given as 50 whole square. Then you will get the answer in mm square. So I am getting the answer is 1963.5. 1963.5 mm square I am getting the answer. Okay, that is the value of cross sectional area. You need to find out the tensile stress. Okay dear, tensile stress you need to find out. So you have to represent as sigma AA. So this means that the axial stress is acting at A should be equal to axial stress is acting at B equal to force per unit area. The force is how much is given here? The force is we applied as how much here? 15 cos 60 we applied. So what is the nature is there? Compressive, means minus 15 cos 60 by area. How much we got here? 1963.5. If you calculate this value, then you will get the answer of tensile stress. So I am getting the answer is minus 3.8197. So what will be the unit here? The unit of force is Newton per mm square. Okay, that is the value of tensile stress is acting at a point of A is equal to tensile stress is acting at a point of B. We are getting the value is minus 3.8197 Newton per mm square. But actually we need to find out the maximum normal stress as well as we need to find out the maximum shear stress we need to find out. Okay, the maximum normal stress. So maximum normal stress, how much is given here? Sigma A equal to, because both values having the same, is it right? So you can take any one. So maximum normal stress is how much is there? Minus 3.8197 Newton per mm square. Again, what we need to find? We need to find out the maximum shear stress. You need to find out the maximum shear stress. Okay, tau is equal to sigma A by 2. The formula is there. Sigma A value is how much is that here? 3.8197 by 2. Then you will get the answer in, so I am getting the value is 1.90985 Newton per mm square. Okay, that is the value of which one here? Axial load is acting. Again, what we need to find here on this figure? First is axial force is acting, second one is bending load is acting. Is it right? Again, we need to find out bending load. You need to find out. Considering bending load, okay dear, let us see the figure. This is section A and section B. At the free end, or it is on the axis, the bending load is acting in a compressive nature. How much is acting here? 15 sin 60. 15 sin 60. Okay dear. So what will be the length? The length of the specimen is 250 mm. Okay. If you want to draw the load distribution diagram, then let us see. Above we can say as outer fiber, below we can say as, below the axis we can say as inner fiber, outer fiber, below we can say as inner fiber. Okay, fiber. Okay dear, again what I am doing here, let us see, we applied which load here? Bending load. Where? At the free end. Okay dear, we are applying the bending load on this specimen. So if you apply the bending load, then what will happen here? So it is above the portion, tensile load is acting. Which load is acting here? Above, tensile stress is acting. Below this component, which load is acting here? Compressive load is acting. Okay dear, here compressive. Again, if you want to draw the free body diagram, let us see. So this one, what we can say here? This one we can say as fixed end. And this one what we can say here? Free end. The above what we can say here? Above we can say as outer fiber. So what is the nature of outer fiber? Tensile nature. Outer fiber. Okay, so how is the nature? Tensile nature. So below what we can say here? The below we can say as compressive or inner fiber. Inner fiber is, how is it here? Inner fiber is compressive nature. Okay here. Again you need to solve the problem of loading stress. Okay dear. The bending normal stress, where here? First at A. At A which force is acting here? At A is tensile force is acting. Is it right? At A, in bracket you have to write down tensile force. Okay, then how to find out this bending normal stress dear? We know very well. We have the formula is for the bending stress is, for bending stress at A equal to M by ZB. Okay, so M is nothing but the moment, how much moment you applied at the free end. How much we applied here? 15 sin 60. So what is the formula is there? Force into length by pi by 32 into d cube. Okay dear, let us see. Sigma BA is equal to force, how much we applied here? We applied the force of 15 sin 60. Okay, 15 sin 60 into length is, how much is that here? The length of this specimen is 250 by pi by 32. D value is, how much is that here? The D value is 50 mm diameter whole cube. Then sigma BA equal to 15 sin 60 into 250. If it is move above 32 pi into 50 whole cube, then you will get the answer of bending stress is acting at a point of A. So I am getting the value is 264. How much? 264.637. 264.637 Newton per mm square. Again you need to find out bending normal stress is acting at a point of B. Bending normal stress at B. So bending normal stress at B. So what is the nature is there? So the nature is compressive. Tell me dear, the bending stress at A is tensile nature, bending stress at B is in compressive nature. Then we have to represent the formula is sigma B capital B. So bending stress at B equal to minus M by ZB. M nothing but minus force into length by pi by 32 into d cube. Okay, then force is, how much is given here? Sigma B force is given as minus 15 sin 60 into length is given as, how much? Length is given as 250 into 32 by pi into 50 whole cube. Then sigma BB. So bending stress at B equal to, so I am getting the value is minus, how much here? Minus 264.637 Newton per mm square. We found out the value of normal stress. Again what we need to find out here? We need to find out the shear stress. Is it right? Then we need to find out the maximum shear stress. Maximum shear stress we need to find out. Then how to find out here? The maximum shear stress formula is tau is equal to, okay, the maximum bending stress at A minus of the maximum bending stress at B by 2. Let us see the maximum bending normal stress minus of minimum bending stress at B by 2. Then you will get the value of maximum shear stress. Is it right here? Then tau is equal to maximum shear stress is equal to tau equal to, how much is there here? 264.637 minus, how much do you hear? Minus 264.637 by 2. If you divide, then again you will get the value of again 264.637 Newton per mm square. That is the value of maximum shear stress. Okay dear, again what we need to find? We need to find out the twisting moment. Third one, consider twisting moment, or we can say as torque. Okay dear. Then which formula we have to use here? For the twisting moment we have to represent as the shear stress tau is equal to T by ZT. Let us see the figure. The same figure you need to draw here. Consider the section A and B. On A and B, the twisting moment is acting. T is equal to 1 into 10 power of 3 into 10 power of 3 Newton mm. So this means that torque is equal to 1 into 10 power of 6 Newton mm. Okay dear, again the diameter is given as 50. If you consider this circular cross section of the free body diagram, then the above the section the tension is acting or tensile stress is acting, the below is compressive stress is acting. Okay, tensile stress is acting above the axis, below the axis compressive stress is acting. Okay, then we have to use the formula of shear stress. Tau is equal to T by ZT. Torque is how much is given here? Torque is given as 1 into 10 power of 6. Okay dear, 1 into 10 power of 6. If bases are same, the power should be added. 3 plus 3 it should be 6 by ZT formula is pi by 16 into D cube. Okay dear, then again 1 into 10 power of 6 into 16 by pi into D value is how much here? So I am getting the diameter is 50 whole cube. If you calculate with the help of calci, then you will get the value of shear stress. So I am getting the value is 40 plus or minus 40.74 Newton mm square. Again we can represent here the maximum shear stress is plus 40.74 and the minimum shear stress is minus 40.74. So the maximum shear stress we can represent as tau max is equal to plus 40.74 Newton per mm square. And the minimum shear stress is how much is that here? Minus 40.74. Minimum shear stress. Minimum shear stress is equal to minus 40.74 Newton per mm square. So we got the value of only twisting moment, but again we need to find out the torque combining these both tensile stress as well as bending stress. Okay dear. Okay, next one. Consider load and moment combined together. Okay dear. So in this equation, how much maximum stress is acting at a point of A we need to find out, and how much minimum stress is acting at a point of B we need to find out. Let us consider at point A. At point A, the maximum stress sigma x is equal to the stress axial stress is acting at a point of A plus the bending stress is acting at a point of A. Let us see, sigma x nothing but sigma x normal stress equal to axial stress is acting at a point of A, bending stress is acting at a point of A. Let us see the axial stress, how much we got it here. The axial stress we got the value of minus 3.8197, minus 3.8197 plus the bending stress value, how much we got it here. The bending stress at A we got the value of plus 637. If you subtract this value, then you will get the value of sigma x. So I am getting the value of sigma x is 260.819 Newton per mm square. That is the value of sigma x. Okay dear. Again, what we need to find out, the shear stress is already given. How much is maximum shear stress is given? 40.74 is the maximum shear stress is given, or we can say as tau xy, or we can say as tau equal to how much is given? The maximum shear stress. Otherwise you can represent as maximum shear stress, or you can represent as tau xy. It's your wish. How much is given? 40.74 Newton per mm square is given. Okay dear. Again we need to follow the maximum principal stress theory. The maximum principal stress. So maximum principal stress, what is the formula is that here? Sigma 1 equal to sigma x plus sigma y by 2 plus under root of sigma x minus of sigma y by 2 whole square plus tau xy whole square. Okay dear, sigma x value is how much is that here? We got the value of 260.819. 260.819. Sigma y value is how much is that here? We don't know, because there is no biaxial stress is acting on this component. For that reason you have to consider as 0. Okay, 0 by 2 plus sigma x value is how much is there? 260.819 minus of 0 by 2 whole square tau xy means the maximum shear stress. The maximum shear stress is how much is that here? 40.74. We know the value 40.74 whole square. So if you calculate by the calci, then you will know about the value. Then you will get the answer is, so I am getting the answer is 266.64. 266.624 Newton per mm square. So I'm getting the value of 266.624 Newton per mm square. Again, what we need to find? We need to find out the minimum principal stress. We need to find out. Okay, dear. Again, the minimum principal stress. Minimum principal stress we need to find. So what is the value is there? Sigma 2 equal to sigma x plus sigma y by 2 minus of under root of sigma x minus of sigma y by 2 whole square plus tau xy whole square. Okay, dear. Then sigma x value is, we know very well, 260.89. Sigma y value is 0 by 2. Sigma x value is 260.89 minus sigma y value is 0 by 2 whole square. Tau xy value is 40.74 whole square. Then if you calculate this value, then you will get the answer. Okay. Let us see. So I am getting the answer is minus 6 point sigma 2 value is minus 6.2123 Newton per mm square. That is the value of sigma 2. Okay. Again, what we need to find out here? Maximum shear stress we need to find out, because we find out the at a point of a maximum principal stress, after that minimum principal stress, after that we need to find out the maximum shear stress we need to find out at a point of A. Okay, maximum shear stress. Okay, dear. Tau max equal to plus and minus under root of sigma x minus of sigma y by 2 whole square plus tau xy whole square. Okay, dear. So plus and minus sigma x value. How much is that here? Sigma x value is 260.819. 260.819. Sigma y value is how much is that here? Sigma y is 0 by 2 whole square. Tau xy value is 40.74 whole square. Okay, dear. If you calculate by the calci, then you will get the answer. So I am getting the answer is 136.624 Newton per mm square. That is the value of maximum shear stress at a point of A. Again, you need to find out at a point of B how much maximum normal stress is acting. So I am rubbing this one. Let's see. So in this equation, at a point of B, we need to find out the value at point B. Okay. Again, what we need to find? We need to find out sigma x. How much tensile stress is acting at a point of B? Axial stress, or we can say as tensile stress. Don't be confused. Axial stress is acting where, dear? At point B, plus bending stress is acting at a point of B. Okay, dear. Axial stress, how much is acting, dear? Same axial stress is minus 3.8197. The bending stress is different. So how much we got this bending stress at B? So we got the value is minus 264.637. Okay, here if you subtract this value, if you add this value, then you will get the answer is sigma x value. I am getting the value is minus 268.4567 Newton per mm square. That is the value of sigma x. Again, here again the same case, sigma y value is 0 and shear stress value is 40.74. Again, let sigma y value is 0 and tau xy, okay, shear stress. So how much is there? 40.74 Newton per mm square. Okay dear, again what we need to find out? Again we need to find out the same maximum principal stress we need to find out. The maximum principal stress, so we have the formula is sigma 1 equal to sigma x plus sigma y by 2 plus under root of sigma x minus of sigma y by 2 whole square plus tau xy whole square. Okay dear, sigma x value is how much we got it here? Minus 268.4567. Sigma y value is 0 by 2 plus under root of sigma x value is minus 268.4567 minus of 0 by 2 whole square plus tau xy value is how much is that here? 40.74. 40.74 whole square. If you calculate the value with the help of calci, then you will get the answer is 6.046 Newton per mm square. That is the value of sigma 1. Again we need to find out the minimum principal stress we need to find out. So if you want to find out the minimum principal stress, you have to use the formula is sigma 2 equal to sigma x plus sigma y by 2 minus under root of sigma x minus of sigma y by 2 whole square plus tau xy whole square. Okay dear, and sigma x value is how much is that here? Minus 268.4567 plus 0 by 2. Okay dear, minus under root of minus 268.4567 minus 0 by 2 whole square plus tau xy is how much is there here? 40.74. 40.74 whole square. Then if you calculate this value with the help of calci, then you will get the value sigma 2. So I am getting the value is minus 274.503 Newton per mm square. So that is the value of minimum principal stress. Again what we need to find? We need to find out the shear stress we need to find out. Okay dear, how to find here? The same formula we have to use. The shear stress. For the shear stress you have to use this formula only. Is it right here? Then tau shear stress maximum equal to plus or minus under root of sigma x minus of sigma y by 2 whole square plus tau xy whole square, plus and minus sigma x value is minus 268.4567 minus 0 by 2 whole square plus 40.74 whole square. If you calculate this value, then you will get the answer is 140.274 Newton per mm square. So that is a value of shear stress. Let us see over here, the maximum principal stress is acting at a point of A, and the minimum principal stress is acting at a point of B. Okay dear, thank you.